Okay, so welcome to part 3 of our math lab for trig identities and the memory hexagon. In page 1, just to recap, we learned how to set up the trig identities hexagon, and we found the 12 quotient identities and the 6 reciprocal identities. Okay, then in page 2, we looked at the product identities and the cofunction identities. And now, before we can look at the Pythagorean identities, I just want to take a second to see how they're derived, why they work, before we look at the shortcuts for remembering them on the hexagon. So in this diagram here of our unit circle, remember, since it's a unit circle, the radius, the length of the radius of that circle is 1. So we'll just jot down here that the radius is equal to 1. And remember also that the angle C here is a right angle because we were given that C is a right angle in our directions. B is a point on the circle in quadrant 1. That's up here in the directions. And when we're labeling triangles, the capital letter angle is always opposite the lowercase letter side. So since this is angle A, from B to C, that's lowercase a. Since this is angle B here, opposite then would be lowercase b. And then angle C is our right angle. That makes the hypotenuse here side C. Okay, and we know that C is equal to 1 because that's the radius of the circle. Okay, we also want to recall, before we get started, our acronym for trig functions. So, ca, toa, right? That reminds us that in right triangles, the sine is the ratio of the opposite over the hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Okay, so our angle x here, the A would be opposite. Okay, then the B with respect to angle x would be adjacent. And then the C is the hypotenuse, which in this case is the same as the radius of the circle. Okay, so in step number 1, it tells us to state the ratio of the length of BC divided by the length of AB in terms of x. So if we look at our diagram here, from B to C, right, that's little letter a, that's the opposite side. From A to B, that's little letter c, that's the hypotenuse. And opposite over hypotenuse, that's the sine. So in number 1, the length of little letter a, that's going to be equal to the sine of angle x. Okay, in number 2, it says to state the ratio of the length of AC over the length of side AB. So looking at our diagram, A to C, that's little b, that's the adjacent side. And then we've got A to B, that's the hypotenuse again, side C, and adjacent over hypotenuse, that's the cosine. So we know that the length of side B is the cosine of x. Okay, now we're going to go ahead, now that we have A and B and we know that C is the radius, that's 1, we can use our Pythagorean theorem that says that A squared plus B squared equals C squared. So as we substitute in from number 1, A, the length of side A is sine of x, so then we'll have sine squared x. And in trig notation, we always put the square after the sine so that we know it's the sine, the whole sine function that's being squared, not just the value of the x. And then we'll substitute in cosine of x for b from part 2. So cosine squared of x. And then substitute for c, since c is the hypotenuse, that's the radius of the unit circle, that's going to be equal to 1 squared, which is just 1. And this is our first Pythagorean identity. Okay, number 4 asks, does the Pythagorean identity hold true in the other 3 quadrants? why or why not. And if you remember on your circle, right, in quadrant 1, both the x and the y are positive. In quadrant 2, your x is negative, but your y is positive. In quadrant 3, both x and y are negative. And then back in quadrant 4, your x is positive, but your y is negative. So will those sign differences make any difference to whether this Pythagorean identity would work outside of the first quadrant? And the answer would be no, it's not going to make any difference, because when you square a negative, you get back a positive. So even if one or both of these values of x, of the angle, were negative, or not the, yeah, if our angles produced a sign value that was negative, the impact is still going to be, by squaring it, a positive. So a positive plus a positive equals 1 is going to be fine. So does the Pythagorean identity hold true in the other 3 quadrants? Yes, it does. And that's because you're squaring positive or negative values always results in a positive. Okay, then 5 tells us to divide each term in the Pythagorean identity from number 3, so sine squared x plus cosine squared x equals 1. We're going to divide each of those by cosine squared. So remember, if I do the same thing to every term in an equation, it's still balanced. So we haven't changed its equality. But when I go to simplify this, sine divided by cosine, that's tangent. So that's going to give me tangent squared x. And then cosine squared x divided by cosine squared x, anything divided by itself is 1. And 1 divided by cosine, that's the reciprocal of secant. So this would be equal to the secant squared x. And that is my second Pythagorean identity. Tangent squared x plus 1 is equal to secant squared x. Okay, then step 6 here tells us to go back to our original Pythagorean identity, so sine squared x plus cosine squared x equals 1. And we're going to divide everything this time by the sine squared. So sine squared x, sine squared x, sine squared x. Everything got divided by sine squared x. Okay, and sine squared x divided by sine squared x, those cancel and leave a 1. Cosine divided by sine is cotangent, so this becomes a cotangent squared x. And then 1 over sine, that's a reciprocal identity for cosecant. So cosecant squared x. And that is our third Pythagorean identity, that 1 plus cosine squared x is equal to cosecant squared x. Okay, so now we'll look at how we can use the trig hexagon in order to remember these identities. So it tells us down here that for each shaded triangle, right, the upper left function squared plus the upper right function squared equals the bottom function squared. And that's just saying that in this triangle right here, okay, where the little arrow is, if you start in your upper left corner, right, sine squared plus cosine squared equals 1 squared, which is 1. If we were to start over here in this triangle in the bottom corner, right, same pattern though, we start in the upper left, so tangent squared plus 1 squared equals secant squared, right? If we do this third triangle here, 1 squared plus cotangent squared equals cosecant squared. So all this work that we did up here to derive these Pythagorean identities, that can be recalled really quickly using that pattern from our trig identity hexagon. Now, often you need to rearrange these identities though to be able to use them in solving equations or verifying trig identity problems, that sort of thing, simplifying expressions. So if we wanted to solve this first Pythagorean identity, sine squared x plus cosine squared of x equals 1, if we want to solve that for sine, we would subtract the cosine squared x to the other side. So sine squared x is equal to 1 minus cosine squared x. Similarly, if I wanted to solve it for cosine squared x, I would subtract the sine squared x. So cosine squared x is equal to 1 minus sine squared x. Okay, then my second identity came from this triangle here, that tangent squared x plus 1 is equal to secant squared x. And I'm going to solve that for tangent squared x by subtracting the 1. So tangent squared x is equal to the secant squared x minus 1. And secant squared x, if I want to get that by itself, right, if I look up here, it's already by itself. So I would have my secant squared x equals tangent squared x plus 1. Okay, and then my last Pythagorean identity started in the center here with the 1 plus cotangent squared x equals cosecant squared x. So 1 plus cotangent squared x is equal to cosecant squared x. So solving for cotangent squared x, I would subtract the 1 from both sides and get cosecant squared x minus 1. To get cosecant squared x by itself, right, that's already isolated over here, so it'd just be the other side, 1 plus cotangent squared x. Okay, and those are the Pythagorean identities.